I have a tutorial here on what's called blackbody radiation or thermal radiation in the context of stars. So a little bit about this term first, because it might not make a lot of sense without some explanation. What do we mean by a black body? What that means in this subject is that I have an object that is a perfect emitter of radiation, so it has no inefficiencies in radiating at any different wavelength. That's a perfect emitter. A perfect emitter has to also be a perfect absorber. So all across the spectrum of electromagnetic radiation, the object is equally able to absorb all the different kinds of light perfectly. So a perfect emitter has to be a perfect absorber, is true because of thermodynamics. And if you think about what a perfect absorber is going to look like, all the different colors of light and all the different kinds of light that fall onto that surface are going to be absorbed and not reflected. So therefore that surface is going to be black. And hence the term black body or black body radiation. All right. White light is made up of all colors of light. We can see the individual colors when white light is passed through a prism or when we look at a rainbow. Light can come in an array of types or forms, which we call a spectrum, and then a spectral curve, which is what's shown here below in figure 1, is a graph that displays the amount of energy given off by an object each second versus the different wavelengths or colors of light. For a specific color of light on the horizontal axis, the height of the curve will indicate how much energy is being given off at that particular wavelength. And figure 1 shows a spectral curve for an object emitting more red and orange light than indigo and violet. And notice that the red end of the curve is higher than the violet end, so the object will appear slightly reddish in color. All right, so a little bit before we dive in further here with the questions. This tutorial is going to talk about colors of light in terms of their wavelength, which is fine for this subject. But fundamentally, the color of light is telling you what the frequency is. That's not all that important for this class, but I just wanted to state it clearly. For the purposes of this class, we can think of frequency and wavelength being exactly interchangeable. When light is interacting with matter, there are some subtle effects, and so what you perceive as like the color red or the color green is actually telling you the frequency of light, not the wavelength. That's fine. All right. So which color of light has the greatest energy output in figure 1? Well, tallest of all is red. Imagine that the blue light and orange light from the source were blocked. What color or colors would now be present in the spectrum of light observed? So we block out blue and we block out orange. So what colors are left? And we still have violet, indigo, green, yellow, and red. So it's our Roy G. Biv minus the O and the B. All right. Which of the following is the most accurate spectral curve for the spectrum described in question 2? So it's taking this and blocking out blue and orange. So if we go through, this has blue, this has orange, and it doesn't look like that shape. This is pretty much blue and orange, which that's not what we're asked, is to be blocked. So the spectral curve missing blue and missing orange is going to be the curve in A. Which colors of light are present in 3B above? So we have mostly blue and orange, and there's a little overlap into indigo, tiny bit of green, tiny bit of red, mostly blue and orange. what colors are present in 3C above, and then would this object appear reddish or bluish? So we've got violet, indigo, blue. Spectral curve is going down, so it's green, yellow, orange, and then it dies off and goes to 0. So it's all colors. So it has all of those colors except for red. And would this object appear reddish or bluish? Well, it's tilted more to the blue end of the spectrum, so it would appear bluish. All right, turn a little bit more towards stars now. This is an astronomy course after all. Different colors of light are manifestations of the same phenomena but have different wavelengths. For example, red light has a wavelength between 650 nanometers and 750 nanometers, whereas violet light has a shorter wavelength between 350 nanometers and 450 nanometers. Stars also give off light at wavelengths outside the visible part of the spectrum, as shown in figures 2a, 2b, and 2c. The two most important features of a star's spectral curve, also known as a blackbody curve, are its maximum height or peak, so where the energy output is greatest, so where does the curve turn over? So it goes from increasing to decreasing, so from increasing to decreasing, so that peak could be steep or it could be broader, but these curves all have a peak. And then the other important factor or feature is the corresponding wavelength at which this peak occurs, which indicates the star's temperature. If the peak occurs at a long wavelength, the star is cooler than a star that gives off most of its light or peaks at a shorter wavelength. All right, and this is what's known as Wien's law. The wavelength at which a spectral curve is peaking is inversely proportional to the temperature. So the higher the temperature, the shorter the wavelength. All right, so for example, if star E and star F, so we're looking at star E and star F in figure 2a. They are the same size and temperature. They will have identical blackbody curves. However, if star F is the same size as star E but cooler, then its energy output is less at all wavelengths, and the peak occurs at a longer wavelength toward the red end of the spectrum. So the less at all wavelengths, that's the consequence of the Stefan-Boltzmann law. All right, which star, looking between star E and F, which star gives off more red light? All right, so which of these curves is taller at the red end of the spectrum? That is star E. Which star gives off more blue light? So which of the spectral curves is taller at blue? Again, that's going to be E. And next question, which star looks redder? Before we jump into that answer, let's see conversation between a couple students. So 2 students are discussing their answers to question 8. Student 1 says, star E looks redder because it's giving off more red light than star F. Student 2 says, I disagree. You're ignoring how much blue light star E gives off, which is quite a bit. Star E gives off more blue light than red light, so it looks bluish. Star F gives off more red than blue, so it looks reddish. That's why star F looks redder than star E. Do you agree or disagree with either or both of the students? Explain your reasoning. So student 1 is incorrect. In this case, student 2 is correct. Everything they said is correct. So no quibbles with them. And student 1 is partly right. star E does give off more red light than star F. If you look at the red part of the spectrum, star E's curve is higher than star F's curve, but that doesn't mean that star E looks red. Star E gives off way more blue light than it does red light. Alright, so which star is going to look redder? That's F. And reasoning. Emits more red than blue light. Okay, so we're going to use these other two pairs of stars here. Scoop things up. All right, we're going to use the blackbody curve shown in figure 2b. For each characteristic listed in the table below, circle the correct response in the column to the right. All right, so we are comparing star E with star C. Which one peaks at a longer wavelength? Well, the peak lines up for both of them, so they peak at the same wavelength. Which has a lower surface temperature? Well, they're peaking at the same wavelength, so they have to have the same surface temperature. It's Wien's law. Which of the stars, E or C, looks red? All right, between stars C and E, which one looks red? Well, they're both peaking in the blue, so neither of them looks red. Which looks blue? Yeah, they are both giving off more blue light than red light, so they're both going to look blue. And which has a greater energy output? So you look at the area underneath the curve for both of those spectral curves. There's more area under the curve for star E. So it has to be emitting more energy as light every second. All right. How must star C be different from star E to account for their difference in energy output? Explain your reasoning. And before we get into that, let's see what our two students think. The peaks are at the same place, so they must be at the same temperature. If star C were as big as star E, it would have the same output. Since the output is lower, star C must be smaller. Student 2 says, no. If its output is lower, it must be cooler. Since the temperature of the two stars are the same, they must be the same size. Do you agree or disagree with either or both of the students? Explain your reasoning. So in this case, student 1 is on the ball. Everything that they said is correct. Student 2 is incorrect in the following. If its output is lower, it must be cooler. That is not true. There are two factors that come into play. One is what's the surface area that's radiating light, and then what temperature is that surface at. If I have more area, there's more light. If I have a higher temperature, again, there's more light. So, just because its output is lower does not mean that star C is cooler. And in fact, since they are peaking at the same wavelength from Wien's law, what this is telling us has to be true is that star C must be smaller. All right. So now we're going to compare stars E and D from this pair of spectral curves. So star E hasn't changed. but now we're comparing it to a new star, star D, with that spectral curve. For each star, describe its color as either reddish or bluish. Well, star E, it hasn't changed, so it is still bluish. Star D, it is peaking at the red end of the spectrum, so it is going to look reddish. Alright, which star has the greater surface temperature? Explain your reasoning. Well, which one is peaking at a shorter wavelength? So star E has a spectral curve that peaks at a shorter wavelength, so E has greater surface temperature. And it peaks at a shorter wavelength. Alright, which star is larger? Explain your reasoning. Alright, so star D we know is definitely cooler, and despite being cooler, it is, if we add up all the area under the curve, very, very bright. There's a lot of light coming off from star D. So for star D to be that bright, despite being at a cooler surface temperature, it has to be the larger star. As giving off more light despite being cooler.